Welcome to all. Myself, Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today, I am going to discuss about semiconductor materials. It is the part of semiconductor optoelectronic course. So, what type of semiconductor materials will be used in semiconductor optoelectronic devices? And how we can have an option to make or choose the semiconductors material. Okay, so this topic will be divided in two parts. The first part I am covering today. So let's start the topic. So semiconductor material. So semiconductor material. So today our focus is about material, not about semiconducting property. Obviously, semiconductors can be defined by two ways. Those material having conductivity sigma is greater than insulator but less than conductors, means if this is the semiconducting material or semiconductor, so the material conductivity will be greater than insulator but less than conductor. Okay, or on the basis of resistivity rho, so insulator, conductor, their resistivity is greater than conductor but less than insulator. And obviously you can define on the basis of energy band gap. So semiconducting material have energy band gap conduction band, valence band. So difference between this bottom of conduction band and top of valence band is known as Eg. So semiconducting material energy band gap value is greater than conductor because conductor don't have any band gap or very small band gap, but less than insulator. Insulator have large band gap. Okay, so based on these three property, either on the basis of conductivity or resistivity or on the basis of energy band gap, you can define semiconductors. These materials are semiconductors. Now I know about semiconductors. Now I want to move, or I want to explain what type of material available to show the semiconducting property. So for that, I have given here periodic tables. Each periodic table contains second, third, fourth, fifth, and sixth group element, not entire periodic tables. Okay. So basically, these groups materials are available to form a semiconductors. The natural semiconductors occurs from fourth group element, like silicon, germanium, or tin. Why? Because these are naturally occurs semiconductor. Like silicon, if you take a silicon crystal, so they will show the moderate conductivity. Moderate conductivity means their conductivity will be less than conductor but greater than insulator. And once you see the geometrical picture of silicon crystal structure, so each silicon atom have four outermost electron, and these four outermost electron will create a covalent bonds with their adjacent silicon atom, so that they will fill their octet. Okay, so this crystal is stable. Okay, so let's start the main thing. So the part of periodic table that's shown here, that is group second, third, fourth, fifth, and sixth element of group. Obviously, once you will see the periodic table, there are mentioned third A, third B, or second B, fourth A, fifth A, sixth A. So don't be confused with A, B, C. Just take the group, okay? Like second group, third group, fourth group, fifth group, or sixth group. Okay? Why? Because based on group only, the outermost electron will decide. And availability of outermost electron is important, okay, to formation of stable crystal structure. Why? Because in silicon, there alone can show the semiconducting property, silica crystal, but there are lot of compound semiconductor like gallium arsenide. So see here, gallium is present in third group, arsenic is present in fifth group. So by mixing of gallium and arsenic, gallium arsenide is also very well known semiconductors. So by mixing of this third group and fifth group, also behave like a semiconductor. Okay. So what is important here? Stability. Gallium have outermost shell electron 3. Once you do the electronic configuration of gallium, you will find that the outermost shell of gallium contains 3 electrons only. But and in arsenic, because arsenic is in fifth group, available in fifth group, so arsenic has outermost electron 5. So these 5 and this gallium 3. So 5 plus 3 8. Now octet is complete. So stability will achieve for this compound. Similarly, uh, indium antimony, or you can say aluminum arsenide, or aluminum indium phosphide. So indium third group element, so outermost shell contain 3 electron. Phosphorus fifth group element, outermost cell will contain 5 electrons. So 5 plus 3 8, octet is complete. Okay, anyhow. So stability will achieve. So stability is also an important parameter for any compound for stable device application. So we will discuss all these things, how we can get a stable, good semiconductors for optoelectronic application. Okay. So elemental semiconductor generally come from group fourth element. Group fourth element means like this silicon, germanium, tin, and lead. Okay. And see here, their outermost orbit containing 4 electron. Okay, 6s2, 6p2. So these two is what? Outermost electron. Okay, so all these atoms have outermost electron 4. Okay, so that's why they generally show the semiconducting behavior. Okay, so in elemental semiconductor, first and most common elements are silicon, germanium, and tin. In fourth, not entire fourth group. If you take a carbon, carbon is not a semiconductor. So, but silicon, germanium, tin will are having the semiconducting property. So the most commonly used semiconductor or most well-known semiconductors are silicon, germanium, and tin. And these elements will show the semiconducting property in their own form, in their natural form. If there is no impurity at all in silicon crystal or germanium crystal or tin crystal, they will still show the semiconducting nature. Okay, so that's why it is written. So in elemental semiconductor, first and most common elements are silicon, germanium, and tin. We also have some binary semiconductor or compound semiconductor. means silicon, germanium, tin are a kind of intrinsic. They will show the semiconducting property by in its natural form, its own natural form. But we also have in semiconducting industry or semiconductor optoelectronic industry have some compound semiconductor or binary semiconductor like gallium arsenide. Okay, so see, gallium is third group element and arsenic is fifth group element. So you can say by mixing of third and fifth also you can get a semiconductors. Okay, so these semiconductors are generally known as third fifth semiconductor, third fifth group semiconductor. Okay, we also have aluminum phosphate. So see, aluminum is also a third group element and phosphorus is fifth group element. Indium phosphide, indium is third group element, phosphorus is fourth group element. So all possibilities are there, one from third group element and one from fifth group. So these are also sometimes called third, fifth semiconductor. Okay, you could also have one element from group 6 and one element from group second. Okay, so third, fifth, so outermost orbit in third group element contains 3 electrons. Fifth group element outermost orbit will contain 5 electrons. So 5 plus 3, 8. Now stability achieved. The same thing can also available. This stability mechanism also available for second and sixth group element. Okay, like zinc selenide. See here, zinc is second group element and selenium is sixth group element. So once you mix zinc with selenium, the octet will complete, stability will achieve. Okay, so that's why such type of semiconductor is known as second six group element: germanium, zinc selenide, cadmium telluride. So for example, some widely used semiconductors in second six group element are zinc selenide, cadmium selenide or cadmium telluride, mercury telluride, mercury selenide. Okay, so all possibility are there. Zinc telluride also, zinc selenide, cadmium telluride. Okay, mercury telluride, all are semiconductor. Okay, so you cannot restrict yourself with on these only fourth group element. This fourth group element is obviously it will show the semiconducting behavior, but for desired optoelectronic application or for desired semiconductor application, sometimes these materials, these fourth group materials like silicon, germanium, or tin, are not having the sufficient conductivity or property to achieve such desired level or such desired strength of performance. Okay, so for removing or for overcome such situation, what scientists thought, why not we mix some other group element, and once they start mixing they also found the semiconducting behavior, and once they add the third group element with fifth group element they will get a semiconducting property like gallium arsenide, indium phosphide, like that, and many more, aluminum arsenide, aluminum phosphide. They expand their thought and they start mixing with second and sixth group element, and they will again get a semiconducting behavior. Okay, and they are even sometimes perform better than the fourth group element. Okay, that's why all these things will happen. Okay, so just I told electronic configuration are very important for outermost cell of or electronic configuration of any elements are important to govern the semiconducting material. So in second group element like mercury have a outermost cell 5d10, so D is complete 6s2. So this 6s2 is present on the outermost cell of mercury. So outermost cell of mercury contain 2 electrons. Okay. Now thallium. See, this is the third group element. So see the configuration 6s2 6p1. So outermost cell contain 3 electrons. Okay. So all the element, if you taking the second group element, the outermost cell definitely contain the 2 electron. If you take the third group element like thallium, it will contain the 3 electron, or even aluminum, gallium, indium, thallium, all will contain the 3 electron. So these outermost cell are very, very important. Okay. So if you are taking a third group element, so definitely you have to choose the fifth group element as a counterpart. So fifth group element have the 5 outermost cell electron. So that 5 and this 3 will create or will make a octet complete. Okay, so that your compound semiconductor will be stable. Okay, that's why the electronic configuration is also important. So that is written here. All element in this third group are the configuration in the outermost cell like 6s2, 6p1 for thallium. For indium, not indium, it is 5s2 and 5p1. If you go to gallium, it is 4s2 and 4p1. Gallium is also third group element. And if you take aluminum, it is 3s2, 3p1. And obviously, if you come to boron, 2s2 and 2p1. So, what you are seeing here, all the from boron to thallium, all the elements have contain the outermost electron 3. Okay, means 3 electrons are present in their outermost cell. Similarly, fourth group element, outermost cell have 4 electrons. All the fourth group, like carbon, silicon, germanium, tin, okay, lead, all have 4 electrons. And similarly, fifth group element, outermost cell have a 5 electron like phosphorus, arsenic, bismuth, antimony. Okay. Now sixth group element like selenium, tellurium, polonium, all have 6 electron in their outermost cell. Okay. Cadmium telluride, zinc selenide. Okay. So combination of this second group element with sixth group element also, it will also create a stable compound because their octet will complete. Okay, and they will also, so once you will measure their conductivity or their band gap, they will also comes under in the region of semiconductor range. So that's why these things are important. So therefore, they from so that they can form a covalent bond sharing 4 electron if you are taking fourth group element. So sharing 4 electron with an adjacent atom to make a octet complete. That is 8 electron cell which complete the octet. If you take one from third group element and one from fifth, there are 3 electrons in the outermost cell in third group element and 5 electrons are present in outermost cell of fifth group element. So once you mix these 3, so 5 plus 3, 8. Now again octet will complete. Similarly for second and sixth group element, the same thing will happen. So here some compound semiconductor band gaps are given, and their lattice parameter and refractive index are also mentioned. So see, the first one is gallium arsenide, and it is showing 1.42 electron volt band gap. Indium phosphide 1.35. So these are the range. Generally, the semiconductors have a band gap from 0.3 or 0.4 to up to 3 electron volt generally. Okay. So see, all these compound semiconductor also showing the band gap value in the range of semiconductor. Gallium nitride, you can say 3.2 or 3 is high band gap semiconductor. So it is showing 3.39. Aluminum nitride, it is generally considered as insulator. In some case, you can treat as a semiconductor. And apart from these, all are well in range of semiconductor band gap, like gallium arsenide, indium phosphide, indium antimony, indium arsenide, gallium antimony. Okay, aluminum nitride, gallium nitride, indium nitride. So their respective band gaps are also mentioned here. Gallium arsenide is having band gap value 1.42 electron. Indium phosphide having band gap value of 1.35 electron. Then indium antimony have 0.17. Indium arsenide have 0.36. Gallium antimony have 0.73. Aluminum nitride has 6.20 electron volt. Gallium nitride has 3.39 electron volt. Indium nitride again 0.65, and the lattice constant are also mentioned. Their refractive index are also mentioned. So why I am showing this? See, these compound semiconductor, while mixing of some third and fifth or second and sixth group element, will also show the band gap which are in the range of semiconductor. Okay, which will show the band gap value which will lie in the range of semiconductor regime. Okay, and their behavior, their refractive index are also very good. So these materials will be useful for semiconductor optoelectronic application. Okay, so these materials. Okay, so I will discuss some more thing about such material in my next video lecture. Thank you for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.